Okay, on to chapter 5. Okay, so Poisson's equation. So when you're doing device modeling, so far we've just talked about, solving Schrodinger's equation with non-equilibrium green functions, and we calculate two things: current. From transmission, we get current and charge. We've developed these algorithms to get charge, but well, the only reason you're getting charge is so you can calculate a new potential through Poisson's equation. And so somewhere, if we look at what you're doing in terms of a little flow chart, you do your NEGEV. RGF is your recursive green function algorithm. You do that. From that, you get your electron density and your hole density. Once you get your electron density and your hole density, you send that to your Poisson solver. Your Poisson solver is going to give you some new potential, phi. That new potential then goes into your Hamiltonian, H minus Q phi. It gives you some new potential that goes into your Hamiltonian. The potential is going to be negative Q phi, right, going from electrostatic potential to energy. That's going to go on the diagonal of your Hamiltonian. And then with your new modified Hamiltonian, you send that back up, right? You construct your new, and you solve for NEGEV again, E minus your new H, G. You get a new green function, and you repeat. And you repeat until this is converged, until your potential isn't changing anymore from one iteration to the next. And then you stop. And so we're going to talk about this a little bit, because although Poisson's equation is 19th century physics, it's actually, to do this correctly, it's just as challenging, if not more challenging, than to do the cool quantum mechanics. And that's why people like to avoid it, because it's a lot of hard work and you don't get much credit for doing it. Okay, so let's just first, what is Poisson's equation? The way you usually see it written is like, we're going to do it in 1D for our examples, corresponding to the one. I'll just leave it at that for the moment. So 1D. And normally you would see something that looks like d squared dz squared 5z is equal to negative your charge, something like this. That would be the way you usually see Poisson's equation. Now the first thing is that, since you're modeling semiconductors, in general, epsilon is not constant. You're going to have different materials, a layered structure like those RTDs we were just looking at, and each different layer, each different semiconductor has a different epsilon. So epsilon is going to be a function of position also. And so when epsilon becomes a function of position, then you're looking at this equation. PdZ of epsilon of Z d dz 5z is equal to, and I'll write out the whole charge term the way we do in semiconductors. So negative Q. And you'll have a bunch of different parts to your charge. One is going to be your ionized donors, your dopants, and your ionized acceptors, also dopants, right? Your whole dopants will be, you've accepted an electron, so they'll be negatively charged. Your electron dopants, you contributed an electron, so you're positively charged, plus your holes minus your electrons. So that's your negative rho on the right side. Okay, that is what determines your charge. Two of these charges, at least for us, the way we're dealing with it, are just fixed. These guys we just assume are just fixed. And not changing as the potential changes. We usually invariably assume what they call complete ionization of your dopants. And for much of what we've done, that's been a very good approximation. When we were doing the 3-5s in the NEMO program, we actually got better results assuming complete ionization and trying to take into account the ionization using the standard equations. Because for heavily doped semiconductors, they go through what people call a MOT, sort of a MOT transition, and all the dopants stay ionized down to liquid helium temperatures. Or if you use the standard sort of equations for whether they're ionized or not, they would all be like no longer ionized, by the time you got below liquid nitrogen temperature. So this has been a pretty good approximation, certainly for all the 3-5s that we modeled. Complete ionization, and so you just replace these Nd plus and Na minus by whatever the doping density is. So these are just replaced by the actual doping density, whatever you doped it at, you just put in there, and that's something known ahead of time. Hopefully you know what the doping is. All right, that's good. But we have to solve this numerically because you have some arbitrary potential, right? Phi is now determined numerically, so 5z is determined numerically, and the same with your P and N. These are coming out of your negative calculation, so it's all numerical. So you have to solve this second order differential equation numerically, and to do that you have to discretize those derivatives. So we're going to talk about discretizing, doing a finite difference form of this solution. So discretizing these terms are trivial. You just, whatever their value is at the given sites, that's what they are. It's just discretizing those derivatives that we got to think a little bit. So here's that derivative expression. Okay, so we're going to start with just looking at a first derivative and then work our way through this. So if we have dz phi of z, we're going to use what's called a centered difference discretization, and that's going to be phi at, so let's say my node is at 0, 0, minus 1, 1. Here's phi. And so the way I'm going to, and I want the derivative at node 0. So this is phi at 1/2. So 1/2 is this sort of in-between point, which I don't know, but I'm just going to formally write it here, right? Here's phi at 1/2 and phi at -1/2. And this is why it's called a centered difference. Minus phi at -1/2 over your discretization length, which we'll call A, like we've always been calling for our lattice constant. So that would be the centered difference form of my first derivative. And so this distance is A. My lattice spacing is A. Seems like a reasonable way to approximate a first derivative, right? Okay, that's good. And so now what do we need to do? Now we need, what we need is this thing above it. So I'm going to sort of, first, so we've just done this. We've just done this part of it. And that goes to this, what we just wrote down. So we replace this discretized expression. So this thing in the red brackets goes into there. And then I'm going to apply my first, you can think of this as an algorithm. If I see this, I do this to whatever I'm applying it to, okay? So now I'm going to have to do it again. And I have ddz acting on epsilon at node 0 times phi at 1/2 minus phi at -1/2 all over a. So again, I have to apply my derivative to that and then use this algorithm on how I go from this differential form to this discrete form. And so that becomes what? That's going to equal. So when I apply this derivative, I take everything back I take everything ahead about a half step, and I subtract everything behind by a half step. So let's go ahead and do that. So I have moving ahead 1/2 step, I have epsilon of 1/2 times moving phi 1/2 a half step up, it's phi of 1 minus moving this -1/2 up a half step, phi of 0. Okay. Yeah. And now subtracting off moving back a half step. So epsilon minus a half times moving back a half step, I have phi of 0 minus phi of -1. And divide by a again, so I end up with a 1 over a squared now, right? Because I already had a 1 over a there to begin with. Okay, so I mean, once I develop this algorithm on how to interpret ddz, I just apply it again. And then I combine terms. So let's copy and paste this. So we combine terms and get our final form. So that's equal to 1 over a squared times epsilon minus a half times phi of -1. Okay, minus quantity epsilon 1/2 plus epsilon minus a half times phi 0 plus epsilon 1/2 phi 1. Okay, now we're doing finite difference, so we actually the only values we know are the values at the nodes that we've defined. We don't know what epsilon -1/2 is or epsilon 1/2. We don't know what's in between the nodes. We only know what's at the nodes. But in finite difference, the assumption is you've made your grid spacing fine enough that a linear approximation between the nodes is sufficient. So to get these in-between values, we just take the average. Right? So to get these fractional values in between the node, we get the average. And so if we, so epsilon 1/2 will be epsilon 0 plus epsilon 1 over 2. Right? Epsilon -1/2 is epsilon -1 plus epsilon 0 over 2. So substituting that all in, we get the final finite difference form for our differential operator. So ddz epsilon ddz phi becomes 1 over a squared times epsilon minus 1 plus epsilon 0 over 2 times phi negative 1 minus epsilon minus 1 plus 2 epsilon 0 plus epsilon 1 over 2 times phi 0 and plus the last term epsilon 0 plus epsilon 1 over 2 phi 1. So that's the final form of what the differential operator looks like in finite difference form. I mean the second derivative in finite difference form. Also note that you know, if you I don't know if we talked about this in 208, but the form of this thing is exactly the same form as you use when you discretize Schrodinger's equation, or I mean when you write Schrodinger's equation with a position-dependent effective mass. So this is what you would do with Schrodinger's equation when you have a position-dependent effective mass. And you can see, I mean, it looks just like our Poisson equation where our epsilon becomes a 1 over m. Okay, so I wrote this all out, but we want to, you know, at the end of the day, you're going to solve this. You know, like when you do something in MATLAB, everything has to become a matrix vector equation. So we're going to turn this Poisson's equation into a matrix vector equation, which is what you do when you do finite differences or finite elements. And so I'm going to go back. I don't want to have to write out all these coefficients in my matrix. So I'm just going to define these coefficients as epsilon minus a half, epsilon 0 or 2 epsilon 0 tilde, and epsilon 1/2 tilde. So I'm going to write those coefficients like that when I write out my matrix. In matrix vector form, our Poisson's equation looks like this. So I've got a minus 2 epsilon 1 and then epsilon 3/2, and then all zeros across the row, and then an epsilon 3/2 minus 2 epsilon 2 tilde, and epsilon, I guess, 5/2, then all zeros, and then a 0 and your epsilon tilde, which are going to be 5/2, and then 2 epsilon 3 tilde and epsilon, I guess, 7/2, 0, etc., etc., and 0, 0. And what you see is you're getting the same block tridiagonal matrix that we've seen before when we discretized Schrodinger's equation, or when we write Schrodinger's equation in our tight binding Hamiltonian, right? It's exactly this, and it's not surprising because we started with the same differential operator. We just replaced epsilon by 1 over m. So in 208, when we discretized Schrodinger's equation, we got this same tridiagonal form. So over here, I'm multiplying it by phi 1, the values at these sites, phi 3, dot, 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 the phi n, and that's going to equal my negative rho 1, negative rho 2, dot, 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 to negative rho n. There's my Poisson equation in discretized finite difference form. And you know, in terms of the form, it looks exactly like what we did for Schrodinger's equation. You always need to worry about boundary conditions. So I guess if this were just a finite chain, that would be all there would be to it, but it's not a finite chain. It's an infinite chain. So somehow you have to truncate this infinite domain into your device region, into the region where you're, at some like out in your leads, your electric field is 0, and it seems like you should be able to truncate it out there. So we need to talk about boundary conditions. And there's two kinds of boundary conditions. So the first, so there's Dirichlet and von Neumann. Any of you messed around with this before? So the first one we'll talk about are the Dirichlet. The Dirichlet boundary conditions mean you just fix the value of the endpoints. Seems reasonable. And the next one we'll talk about von Neumann, you fix the value of the derivative. Okay, so Dirichlet is, when you first start doing this, it's always probably the one you feel most comfortable with. It seems to make sense. You just fix the value of the endpoints. It turns out they're really not as nice as von Neumann boundary conditions. But we use them for a long time. So let's just talk about them and then talk about what happens and why you don't want to use them. Okay, so for Dirichlet boundary conditions, the first problem is you need to know what value to fix those end nodes, and that's really where the problem lies. You need to know ahead of time somehow. You need to know phi 1 and phi n, because that's what you're going to fix. But let's assume you know them. Actually, a better way to do that is to, the way I've always done it, say you've got your device region that goes from 1 to n. So here's 1, here's n, and then you add sort of a fictitious node 0, a fictitious node n plus 1, and you say you know the values at 0 and n plus 1. So you know the values there, and you're going to make use of that information to truncate this system of equations. Because really, when you go back and look at this matrix, this should be over here, epsilon, what should it be? 1/2, I guess, right? And it should be multiplying by phi 0. That epsilon 1/2 should be multiplied by phi 0 there. So if we know the value of phi 0, we can move that term over to the right-hand column. And that's what you do. So this, if we look at this row here, so if we look at this row, our first row, which is going to be affected by this boundary condition, there should really be a phi 0 sitting up here, which multiplies that epsilon 1/2, right? But the boundary condition is you fix the value of phi 0. So that row becomes epsilon 1/2 tilde phi 0 minus 2 epsilon 1 phi 1 plus epsilon 3/2 phi 2 equals negative rho 1. But since you know phi 0, you just move it over to the right-hand side. So this term just gets moved over here, and so your rho 1, you just end up modifying that right-hand side of your equation. Nothing happens over here to epsilon. What's in your matrix remains the same, and you modify your right-hand vector. So if we go back and look at this equation, this becomes negative rho 1 minus epsilon 1/2 times phi 0. And that's your boundary. That truncates your system of equations. And you do the same thing over here. So this would be minus rho n minus epsilon. Oh gosh, what would this be?
1 plus 1 by 2.
Yeah, that would be what it was. This is lousy notation. 2n plus 1 over 2 times phi n plus 1. Right, that's what would be added or subtracted to that term down there. And that's what you do with von Neumann boundary conditions. So it's really easy to implement, and that's why when people first start, that's what they want to do, because it seems pretty simple. Problem is, the hard part is getting phi 0 and phi n plus 1 correctly. And you think, what's so hard about that? Well, so how would you go about getting phi 0? So I mean, you need something to look at. So you've got some, device in some region off on the left. The electric fields have died down. Some region on the right. So over this entire region, say you're solving Poissons equation, right? So you're solving Poisson throughout all of this region where the electric fields are not zero, right? Where the potential is varying as a function of position. And then over here, you've got some Fermi level on the left and some Fermi level on the right. So you've got your Fermi level on the left, your Fermi level on the right, mu left, mu right. And what you know, we said we know our doping density. Right? That's a given. You know your doping density. And since the electric fields are zero, you know that, well, the doping density has got to equal the electron density, because these lead regions have got to be charge neutral. Right? Because the dopants are positive, the electrons are negative. So that tells you, so if you know the doping density out there in those regions, you know the electron density. And then what you have to do is figure out what mu L and mu R are. Right? And so that's sort of doing the usual calculation of the charge density backwards, where you actually know the charge density. Right? That's just given by ND. And that's, say, in our little chain model, and it'd be integral 2 pi. And say we have a two-dimensional cross-section. I haven't really talked about this. But, if your potential is only varying in one direction, by implication, you have an infinite cross-section in x and y if your potential is only a function of z. And so we have to integrate over the transverse momentum, as we talked about, whatever, chapter 3 or something. Trace A JJ times your Fermi factor, say in the left lead. Well, you know N, you know the spectral function, because it's just a flat band region of your left lead. Right? You just assume it's an ideal, your ideal lead, an ideal wire, nothing changing back there. What you're trying to find is this. That's what you don't know. And so you set up some iterative algorithm until you finally get mu. Once you have mu, then you know where your conduction band is here, and then you set this. If you're doing a sort of full band calculation, your band edge is going to occur at some strange energy like -5 eV or something, depending on whatever your full band parameters are. And they're not, they can vary however people set them up, or it could be +2 eV. And so you set the potential here so that this distance is whatever it should be. You choose your potential. There's a couple different ways of doing it. You could just let EC be whatever it is that comes out of the full band calculation and then set mu, or you can use mu as your reference and then just set a potential here so that you get this distance correctly, because this potential will just rigidly move your band up and down, right? It goes on the diagonal, your Hamiltonian, it just rigidly shifts what you call your band edge. And then over on the right-hand side, and let's keep it simple, then you got your band ending region. Over on the right-hand side, let's keep it simple and say that the doping is the same in both the left and the right. And so this difference is, by definition, your applied bias. So the Fermi levels are split by the applied bias, which means that this, the difference in the potential in this case from here to here is also, this is going to be whatever the potential was in the source over here for this boundary condition, your potential on the left, let's see, plus, so this I'm going back and forth between electrostatic potential and energy potential, plus your applied voltage. Right, when it's voltage I add, when I go to energy I have to introduce that negative Q, VA. And then if the, and this is a simple case, it could be if the dopants are different, then there'll be an extra potential over here to make sure, because the difference in the Fermi levels are fixed, but if the dopants are different here, then I'm going to have an extra potential drop, like in a PN junction, right? Where in a PN junction, your Fermi level is flat, but there's a big change in the potential as I go from one side to the other. PN junction is a classic example, right? In PN junction, you've got a flat Fermi level in equilibrium, and you've got one side that's p-doped and one side that's n-doped. So when you go from one side to the other, you drop by that built-in voltage due to the dopants. And so the same kind of effect happens here. So it's, can be kind of tricky choosing your potentials. But the real problem, you can do that, that's fine. But the real problem is that then when you go and you fix your potentials, so now this potential here and here is never going to move. That's fixed for all time. And then you send this off to your Poissons equation, and you start self-consistently doing everything in between. And what invariably happens is you get a potential profile that looks like this. So the first node, there's a discontinuity. And then, say if I'm doing your FET, you'll have your channel region, other discontinuity going either up or down. So if I draw that all together, you invariably getting something weird happening right at that last node or a couple of last nodes, like that, due to this fixing the potential at the end. Because the self-consistent calculation never quite matches up with the perfect ideal lead that you use to approximate this potential with in the first place. Right? The ideal lead has everything is just a perfect plane wave, but there's always some reflection, and so the charge density is never quite as uniform as an ideal lead. So there's always something weird going on at the end. So, for years we used this boundary condition when we were doing the NEMO program, and always the first node or two looked weird. And of course, so when we published this and made our plots, we only included this much of it, and it looked really great because the ends always looked really weird. But we were using our boundary conditions with an I eta through out here, so nothing, all this stuff way back there really didn't matter in terms of the transport. But it is kind of weird, it is kind of unsettling when you see that. So this is really not the boundary condition you want to use. And this is why you don't want to use it. So to avoid this, what we really want to do is use von Neumann boundary conditions. And here you set the derivative of the potential to a fixed value in general, but we set it to 0. So on both ends, we set the derivative of the potential to 0. So that's what we do. So how do you do that in a finite, in this finite difference form? How do you set your derivative to 0? Well, again, you do the same thing. You introduce these fictitious nodes, 0 and n plus 1. That's the way I like to do it, at least. Makes life easier. So you've got, 1, 2, 3, dot, dot, dot to n. Then you introduce your node 0 and n plus 1. And, our derivative, ddz, just means that if that's 0, that means that phi 0 equals phi 1. When I take the difference, I get 0. I get a finite difference. It just means the difference is 0. So I just set phi 0 equal to phi 1. And so if we go back and look at our matrix and see what happens when I do that, here's phi 0 is multiplying this term here. And I set it equal to phi 1. That means I just bring this term here, and I add it on to that term there. So instead of modifying the right-hand side stays unaffected. Now I actually modify those upper and lower corner diagonal elements of the matrix itself. And if phi 0 equals phi 1, I can just move it onto that corner block because I'm already multiplying this corner element by phi 1. So I just add it in there, and my corner block then becomes modified to, so 1, 1 element, or the first row, becomes epsilon of a half minus 2 epsilon 1 times phi 1 times phi 1 plus, and that's the only change. That's the corner block that gets modified. Nothing else changes. Phi 2. Okay, that's what the first row becomes, and the only change is in this corner block. So here's the change right there. This is it. That's the only thing that gets changed. And the same, the last, so that's the last row and the nth row. Same deal. I guess. Let's see if I can do that. So that would be, what would that be? That would be, oh gosh, it's painful notation. Epsilon, what, 2n minus 1 over 2 times phi 2n minus 1 plus the quantity epsilon, I guess that would be 2n plus 1 over 2 minus 2 epsilon n times phi n is equal to negative rho n. And again, the only block that got modified, the only thing that got modified is right here. The lower corner element. And this is just from setting phi n plus 1 equal to phi to n, and then folding it back onto the matrix. You set phi 0 equal to phi 1, then we can fold it back onto that corner element. Same with phi n plus 1. Fold it back onto the phi n block. Okay. Now these boundary conditions are really nice. So how does this work? You don't, for one thing, if you're using von Neumann, oh, what time is it? Oh wow, how time flies. So with these boundary conditions, you don't need to do any pre-calculation of mu left and mu right. And because of that, what we started doing a long time when we moved to these boundary conditions is we set mu left as our reference energy. So mu left is used as a reference energy. So we've got, here's our energy axis. Here's 0. And in every simulation, that's mu left. And then, and also once you set mu left, that automatically fixes mu right too. Right? Since mu right is always going to be equal to, what's it going to be equal to? Anyone tell me?
Left plus EE.
Well, a stupid minus sign. Negative Q times the applied bias. I'm applying bias to the right-hand side. Okay, so this distance is always this negative. So that's fixed. So we know immediately where our Fermi levels are in the left and right lead. And then you just send this into Poisson's equation, and because it forces, a zero field boundary condition, right? The electric field is a derivative of the potential. A zero field boundary condition. And the zero field boundary condition enforces charge neutrality in the leads. So over here in the leads, this thing is automatically going to float until it finds its happy charge neutral region. And the same thing happens over here. The band just floats around during the iteration until it finds its charge neutral position. And you don't have to do any pre-calculation like you do in the Dirichlet boundary conditions. So you just, your Fermi level on the left is always 0. Your Fermi level on the right is always negative QVA. And you send this in, and it floats around until it converges and finds its happy spot where you have charge neutrality in the leads. So these boundary conditions, people call them zero field boundary conditions. They're trying to enforce charge neutrality because that's when you have zero field, and they'll try to enforce charge neutrality overall, because the only way I can have zero field is if the whole thing is globally charge neutral. And they're trying to enforce charge neutrality in your leads. And so these are really nice. And this is what we do. And you don't get any funny stuff going on at the ends, because what they're enforcing, and what they enforce really well, is flat bands here at the end. So you will always get very flat bands at the end, even when you shouldn't. These always make it look really nice and flat, even when you truncated your device, made your device too short, and the fields really physically shouldn't have gone away by then. You will always get zero field at the end because that's your boundary condition. So you still have to be careful. You still need to make your simulation domain large enough so physically the fields could have decayed away by the time you get to the end. Okay, I get.
Like I have set only 2 points equal, right? I mean,
Yeah.
2 points potential equal. So why?
Well, you're not setting the potential. You're setting the derivative. Oh,
So, yeah.
Yeah. Okay. Well, I mean, you mean like setting 0 equal to phi 0 equal to phi 1.
Yeah, but why that should affect for a wide range?
Well, your boundary conditions always affect stuff, right? I mean, you're enforcing it's like the different, I mean, think of, it's funny, what we know are quantum mechanics. You're a hard wall boundary condition in your particle in a box state versus an open boundary condition. You get completely different solutions. So one is like a hard wall boundary. It is different, but I mean, if you make your lead regions far enough, so physically your fields are decaying, throughout the whole device region, you're going to get pretty much, the same answer to within numerical accuracy. You'll just get a little funky stuff at the ends that are different, and if you use your eta and all these generalized boundary conditions, what's going on at the very end of your simulation domain doesn't matter. But these are much nicer. And that's what we use. So I guess, once again, but we'll meet again on Monday. So we'll continue on Monday and talk about, and after you set these up, how you go about solving them to get them to converge.